Alkanoates and Ethers. The functional group in an alkanote is COOR, and again that dash there shows a bond, and is also known as an ester group when R is any alkyl. So here's the alkyl, and the whole thing here is an ester group. An alkanote is formed when an acid, and here's our acid over here, and an alcohol, here's the alcohol, react, and a water molecule, and that's what we have in the black box there, is removed. So once again, here's the alkanote, the ester group, where here's an alkyl, and we have the acid and alcohol reacting. We get our alkanote over here, and then we have water that's pulled out of it. Here's the reaction from the previous slide, along with its condensed, and then the structural formulas. Two more examples. We have ethyl acetate down here, and can you see the difference? Your methyl acetate is H3, ethyl is H5, and then you have methyl propionate. The IUPAC naming of alkanotes will be discussed in a later unit. And let's look at the ball and stick model. Have a CH3 here, a CH3 over here, and then here we have our center carbon, and it's got a doubly bonded oxygen and a singly bonded oxygen. Some physical properties. Alkanotes are polar compounds, but not as much as alkanols. They are soluble in water as they bond to water with hydrogen bonds. The degree of solubility is less than that of the acids and alkanols which comprise them due to the lack of an OH group, right? That left to form a water molecule. Their boiling points are lower than the boiling points of the acids and alkanols which comprise them. Alkanotes have a pleasant smell and are found in perfumes and artificial flavors for food. Essential oils and pheromones are alkanotes. Due to the sweet aroma associated with alkanotes, they are widely used in the perfume industry and as essential oils and pheromones. Here we have methyl salicylate over here, looks like berries there, and propyl ethanote. And where is this coming from? Pears. Alkanotes are responsible for many aromas, including those of many fruits. So here's some examples. Okay, benzyl acetate, pears, strawberry jasmines, and we'll just skip down a few. Amyl acetate, bananas. Then we have nail polish remover. All right, this is not something you want to smell for too long. Then we have orange flavors, pineapple, apple and honey, and then oil of wintergreen. In nature, fats are triesters of glycerol and long-chain acids. And remember, alkanotes and esters, sometimes people use them simultaneously. Fruits and flower extracts have alkanote functional groups in them. Soap making via saponification. Soap making starts with fats and oils. Fats and oils are triesters of fatty acids and glycerol. The fats or oils are treated with strong bases like sodium hydroxide or potassium hydroxide. This will hydrolyze or saponify the fats and oils. Breaking down the ester linkage in the fats with the help of sodium or potassium hydroxide is known as saponification, which we'll show on the next slide. With the sodium salt, a hard soap is produced. With the potassium salt, a soft soap is produced. Soap making. This will show the molecules involved in this process. We start with a triglyceride or fat, and here in that oval, that's the ester alkanote group. And over here, we have a long hydrocarbon chain of the fatty acid. You've got a carbon at each vertex. The sodium hydroxide is added to start the hydrolysis saponification reaction. And let's look what happens to these atoms. Well, the sodium and oxygen combine with our long hydrocarbon chain, and this is the soap. This is the sodium salt of the fatty acid. Where does the H go? H goes over here to combine with the CH2s and the CH, and it makes glycerol. Soap made with sodium hydroxide, that is hard soap, will have a higher melting point than soap made with potassium hydroxide, soft soap. However, The solubility could be the reason sodium salt soaps are hard and potassium soaps are soft. Sodium salt soaps are less soluble in water than potassium salt soaps. The reason for this could be explained by the difference in charge density of the sodium ion and the potassium ion. The smaller size of the sodium ion makes the charge density greater. The greater charge density causes the sodium ion to be more strongly attached to the fatty acid than the potassium ion. If we also examine the enthalpy of hydration for both ions, we find that sodium has a higher value than potassium, meaning that sodium is less likely to hydrolyze. Another factor in the difference between a hard soap and a soft soap depends on if there are excess fats during saponification. The leftover fats will plasticize, making the soap hard. The source of fatty acid can also impact whether the soap is hard or soft. Animal fat will give a hard soap, while vegetable oil will form a soft soap. The polyunsaturated triglycerides have weaker intermolecular attractions. Fire extinguishers used to put out grease fires use saponification to put out the fire. Spraying the fire extinguisher turns the fats and oils to soap, making it no longer flammable. The reaction happens to be endothermic, further enhancing the effectiveness of the fire extinguisher. The reaction draws heat from the flames, lowering the temperature of the fire. Billions of kilograms of polyester are produced annually. Major types are polyethylene terephthalate, better known as PET, certainly a lot easier to pronounce, acrylate esters, and cellulose acetate. Phosphodiester bonds form the backbone of DNA. Probably a lot more important than polyester. Alkanoates are used as solvents in plastics, resins, and lacquers. Aspirin is an alkanoate of salicylic acid. Omega-3 supplements are ethyl esters of fatty acids. The common name of this molecule is triglyceride, the main constituent of animal and vegetable fat. So here's our fatty acid chains over here in the light blue, and here's the glycerols. And here's a very simple functional group, the ether functional group. It's an oxygen atom that forms single bonds to two carbon atoms, which could be part of a chain or group. For example, an oxygen atom single bonded to two alkyl groups is an ether. Here's some examples of ethers. We have the oxygen singly bonded to a carbon on either side, and these are our alkyl groups. Diethyl ether. Okay, we start here pretty simply with the O single bonded to a carbon. Then you have two CH2s and a CH3 hanging on the end. And here it doesn't have to be symmetric. This is an ethyl methyl ether. Here's oxygen. And finally, we can have a ring with tetrahydrofuran, or THF, somewhat easier to pronounce, where we've got the oxygen single bonded to two carbons over there. Ethers are highly flammable and are used as solvents for organic synthesis, extracting media for esters, gums, paints, lubricating oils, plastics, lacquers, hydrocarbons, and many other similar substances, antiseptics, and anesthetics that can induce euphoria and sedation.